So we're going to revisit conic sections for the last time. This time we're going to revisit conic sections on the polar plane. In the past, we talked about conic sections with the center. Notice when we graphed these on the xy plane, we said here's the center, here's how far we go from the center to the major and minor vertices, or this is how far we go from the center to the vertex, or if we were talking about a parabolic, then we were worried about the vertex. In polar coordinates, we are more concerned about the focus. And so we're going to define everything in terms of the distance from the focus. So we get some fixed line L, and we have some point F that is not on L. Then we're going to talk about the eccentricity. The eccentricity is defined as the distance from some point P to the point F, which is the focus, and some point P to the line L, where the point P is not on L. The line L in particular is what we call the directrix. So here's our point P, here's our point F, and this is the radius. This is line L, which is also the directrix, and we know that the directrix is going to be halfway between there. So that distance traveled between the point P and my line L is going to be d, distance d, and r cosine theta. The reason it's r cosine theta because if this angle is theta, then the x part of it, the distance we traveled there, would have been the cosine of theta is equal to x over r. So r cosine theta would be the distance x that we traveled. That gets us to this equation right here, which is E, eccentricity, is equal to r divided by d plus r cosine theta. If we then take that equation, E is equal to r d plus r cosine theta, and we solve for r, which means we multiplied both sides by d plus r cosine theta, d plus r cosine theta, then what we'll end up with is E times d plus E times r times cosine theta is equal to r. If I bring everything with an r to one side of the equal signs, then I'm going to get E times d is equal to r minus E r cosine theta. So factoring out an r and dividing by that, so E d is equal to r, 1 minus r, or E cosine theta. We're going to get E divided by E d divided by 1 minus E cosine theta is equal to r, which is how we got this equation here. So with these type of conics, which are on the polar axes, then we're going to be looking specifically for sines and cosines. Notice that all of these equations have E cosine or E sine. So if we are looking for E cosine and E sine, the other thing that we are looking at is if this is a minus, then our directrix is x is equal to a negative d. If this is a plus, then it's a plus d. And so if you are using cosine, then we know that whatever's happening is my directrix is over on the perpendicular to the x-axis. Now if you see sine, then our directrix is going to be perpendicular to the y-axis. So keeping that in mind, we're now going to look at a little bit more information here in terms of the eccentricity. So if I have an eccentricity that is between 0 and 1, then I have an ellipse. Not only do I have an ellipse, I can tell you the length of the major axes, and I can tell you the length of the minor axes. if my eccentricity is equal to 1, then I have a parabola, and the focal diameter is 2d. What the focal diameter is when we're talking about graphing a parabola, if this is the location of the focus, then the focal diameter is from side to side through the focus. So that is your focal diameter. That's also going to tell us, our focal diameter is also going to tell us the distance from the focus to the vertex. Now, my last one is when I have E is greater than 1. If E is greater than 1, then what I have is a hyperbola. So here is E greater than 1, and I have a hyperbola. The transverse axis is along the length, has a length of 2ED over E squared minus 1. The conjugate axis is the 2ED square root of E squared minus 1. Now we want to think of this as being, because this is the transverse axis, that's like saying 2A. And if this is the length of the conjugate, this is like saying 2B when we were doing it in the xy plane. So if I'm asked to find the type of conics, the location of the directrix, the location of the vertex, focus, and focal diameter if appropriate, the first thing I'm going to do is determine whether or not I have a sine or a cosine. Because I have a cosine, that means that my shape is either going to be in this direction, or it's going to be looking like this, or it's going to be our axis of symmetry, or our transverse axis, or a major axis is going to be along the x-axis because of the fact it's cosine. Now, I have those relationships. I'm going to go back up to the relationships and determine what I have. So the equation that I had was R is equal to ED 1 plus or minus the cosine of theta. Excuse me, it is plus or minus E cosine theta. So looking by inspection, I'm looking for this number in front of the cosine. This number in front of cosine is 1. If that number is in front of cosine is 1, that means E must be 1. That tells us that 1 times D must be equal to this numerator number, so that must be equal to 2. That means D is equal to 2. So I know the distance from my focus, and I also know whether or not where the directrix is based on these relationships up here. Now if you recall, because this is a minus, just like the one I have, then my directrix is x is equal to negative d. So that tells me down here that my directrix is at negative 2. So I'm going to put my negative 2 in there. So here's where my directrix is. X is equal to negative 2. What I remember from above and the way that we define them, theorem 11.12, is that it will have its focus at 0, 0. So its focus is at 0, 0, and that's going to be true on all of these. So the focus is at 0, 0. That tells me that my directrix, actually I'm going to make this a little bit bigger so I can see it a little bit easier. So I'm going to move my directrix slightly over, and I'm going to do it like this. I'm going to make these each worth 1. So 2 of them will be equal to 1. That way I can see it a little bit easier. So anyways, here's where my directrix was. It was at x is equal to negative 2. Now, if this is where my focus is, which is at the origin, and this is my directrix, then my vertex is the halfway mark. So this is where my vertex must be, because it's halfway between it. It also tells me, if I look from above, the way that we defined it by theorem 11.2, is that at the focus, I have a diameter. So my foci diameter Helps if I can spell it. D foci diameter is equal to 2 times D. So that tells me right here at the focus, I'm going to go out 2 in each direction. So remember, these were worth 2 was equal 2 squares were equal to 1. That's where how far out I'm going to go for my parabola. So going through my vertex and going through the 2 values for the foci diameter, that is what my graph looks like. So there is my location of my vertex. My vertex is at -1, 0. My directrix is at x is equal to -2. My focus for all of these is at 0, 0. And that's what my conic looks like. As I take a look at my next example here, it has to be in the form ED 1 plus or minus the sine, oops, needs to be E there, 1 plus or minus E the sine of theta. Now I have this 2, it's not set to 1. So what I'm going to do is I'm going to get that to be 1 by dividing each one of my terms within my fraction by 2. Divide this by 2, divide this by 2, and divide this by 2. When I do that, I've got r is equal to 3 over 2 divided by 1 plus the sine of theta. Oop, I missed my 1/2 again. Man, I'm missing E today. So 1/2 the sine of theta. This coefficient is what E is, so E must be 1/2. The numerator is E times D, so E times D is equal to 3/2. E is 1/2, so 1/2 D is equal to 3/2. Multiplying both sides by 2, I get D is equal to 3. Now if I go back up to theorem 11.2, it tells me that my directrix is going to be positive because it is a positive or a plus sign. So my directrix, and again I'm going to do this, here's 1, 2, and 3. Here's where my directrix is. It is at y is equal to 3. My first foci is still at 0, 0. And I say first foci because I know that since E is equal to 1/2, that tells me, again, if I go up to theorem 11.12, that if E is equal to 1/2, this is an ellipse. So I have an ellipse, so I have 2 foci. Now, if this is an ellipse, then from above I have this formula that says the length of my major is equal to 2ED divided by 1 minus E squared. So what I'm going to do is I'm going to put in the numbers that I know. So this is going to be equal to 2. E is 1/2. D is 3. 1 minus E, which is 1/2 squared. So this is going to be equal to 3 over 1 minus 1/4. If I multiply everything by 4 to get rid of the 1/4 in the denominator, then what I'm going to get is I'm going to get 12 over 4 minus 1, which is 12 divided by 3, which is equal to 4. Now that is the length of my major. So from side to side, I have a length of 4. That means from side to side it's a length 4. That means from the center it is 4 divided by 2. So in other words, from the center I would have gone 2 in each direction. So now let's find where the vertex is. Once I find out where the major vertex is, one of the major vertices, then I'll be able to go from there to the other vertex, and then I can also find my center. So the way I'm going to find my vertice is I'm going to start with a chart where I'm solving, I'm going to input theta and I'm solving for r. So r is, again, this equation. Let me clear up some of my drawings over here, my colorizations. So r is this. So this is the equation in which I'm going to put in theta. So let's put in theta of, because I want to know where my vertex is. Let's put in theta of pi over 2. So we put in theta of pi over 2, we get 3 over 2 plus the sine of pi over 2, which is equal to 3 over 2 plus 1, because the sine of theta is, the sine of pi over 2 is 1. So I end up with 3 over 3, which is 1. That tells me that my vertex is right there. It is at the point 1, 1. And again, remember my distance of the major length was 4. So all I have to do is count out 4. 1, 2, 3, 4. So here's where my other vertex is. So it is at the point, sorry, this should be the point 0, 1. This is the point 0, negative 3. Halfway between these two is where my center is. So my center is at the point 0, negative 1. Now I do have to figure out how far over in each direction I'm going to go on my minor. And the way that I'm going to do that is I'm going to go back to my definition, my theorem, 11.2, and with an ellipse, the minor axis length is going to be equal to 2ED divided by the square root of 1 minus E squared. So this is going to be equal to 2. E is 1/2. D is 3. The square root of 1 minus E squared. So this is going to be equal to 3 over the square root of 1 minus 1/4. So this is going to be equal to 3. I'm going to take 1 and subtract off 1/4, and I'm going to get the square root of 3 over 4, which then gives me 3 over the square root of 3 over 2, which then gives me 6 over the square root of 3, and if I feel like rationalizing, I'm going to get 6 root 3 over 6, or excuse me, over 3, which gives me 2 root 3. So that is the length, total length from side to side of my minor axes. That means from the center, I'm going to go the square root of 3 in each direction. So if I come back over here, the square root of 3 is bigger than 1, but less than 2, so about 1 point something. I put that in my calculator and I get that. So here's where my ellipse looks like. So here is the equation, or here's the graph of my ellipse. Now, let's look at my next example. In my next example, I have to determine, is it in the correct form? And the answer is yes, it's in the correct form, because what I have is 1 plus or minus in the denominator. Because I have 1 plus or minus in the denominator, that means that this must be E. So E is 3. I go back to my definition in theorem 11.12, and that tells me I have a hyperbola. So if I have an hyperbola, then my directrix is going to be ED is going to equal to 4. 3 times D is equal to 4. That means D is equal to 4/3. Now, because this is a plus, that means that my directrix is going to be a positive x. So my directrix is going to be at, again, I'm going to do this as ones So you know what? I might make these a little bit larger. I'm going to make 3 of them to be 1. That makes it easier when I'm putting in my directrix. So my directrix is at 1 1/3. So here it is, 1 1/3. X is equal to 1 1/3, or in other words, 4/3. That's where my directrix is. Right here is where one of my foci are. Now remember, because we're in polar coordinates, and though my graph is an XY plane, because we're in polar coordinates, one of the foci has to be at the origin, or not the vertex. Yeah, the foci always has to be at the origin. So what I'm going to do now is I'm going to figure out what the length of my major, or my transverse, and I go back to Theorem 11.12, and the length of my transverse is 2ED over E squared minus 1. So 2 times 4, ED is in the numerator, and then E was 3 squared minus 1. So I'm going to get 8 over, and then I have 3 squared, which is 9, minus 1, which is 8. So that tells me the length of my transverse axes is going to be is 1. That means from the center, I'm going to go 1/2 in each direction from the center. I'm also going to find the length of my conjugate axes. The length of my conjugate axes is going to be E2ED divided by the square root of E squared minus 1. So I have 2 times 4 over 3 squared minus 1, the square root of it. So I get 8 over the square root of 8, which if I rationalize is going to be 8 square root of 8 over 8. So I end up with just the square root of 8, which is equal to 2 root 2. So that is the length of my conjugate axes. That's from side to side, so that tells me from the center I'm going to go the square root of 2 in each direction. Now remember, if this is a foci right here at the origin or the pole, that means my hyperbola must be running, my transverse axes must be on the line y is equal to 0, because that's where my focus is. Remember, my focus is always on the transverse axes. And not only that, but my parabola has to cup or hug the focus. So I'm going to figure out what my vertex is by, again, doing the theta and the r. I'm going to start out with 0. So if I put in 0, I'm going to have 4 over 1 plus 3 cosine of theta. That gives me 4 over 1 plus 3, because the cosine of theta is 1. So that gives me 4 over 4, which gives me 1. So that tells me where my vertex is. My vertex is at the point 1, 0. So if that's where my vertex is, and the distance from my vertex is my focus, and the fact that the length of my transverse axes, helps if I put that in the right place. My vertex, because remember I was doing it in terms of 3, so let me go back here. Here's where my vertex is. My vertex is at 1, 0. I have a length of 1, so my other vertex must be over here, which is at 2, 0. My focus, my other focus, is also a distance of 1. So here's where my other focus is. So I have a focus at 0, 0, and I have a focus at 3, 0. And remember, when I'm doing a parabola, I'm going to do a box. My center is halfway between these two, so here's where my center is. And I'm going to draw my box. So in each direction, I'm going to go 1/2 in the x. In each direction in the y, I'm going to go a little bit more than 1 because it's a square root of 2. So a little bit more than 1 square root of 2. So about 1.4. I'm going to go here is 1. Here is 2. So about 1.4 is probably about right there. So, and then the same thing in the other direction. So here is 1. Here is 2. So about 1.4 is about there. This is what my box looks like, in which my asymptotes go through. Sorry, I couldn't talk and draw at the same time. So here's what my hyperbola looks like. It looks like this on this side, and then this on this side. So there is graphing conics in polar coordinates with r equals. I probably should have used polar graphs instead of xy planes in here, but still not too bad. Now I can rotate my conics when they're in polar form as well. And here's the equation right here to graph these with the rotation. I still have eccentricity, but I have these other numbers in which I have to worry about. I have to worry about, just like in my rotations, I had to worry about theta. And now I'm also going to worry about phi. Phi, phi, pho, fum. It's so much fun. So as we take a look at this, it's already set up for us. It's already set up with phi, and it already is set up with theta. And phi is your rotation. So that tells you how far you're going to rotate. And so we're going to rotate my axes 60 degrees. And so it's going to look something like this. Let's see if I can do this. It's going to rotate something like 60, let me see, 60 degrees. So something like that. And then something, let's try this again. Something like, let's try this one more time. Okay, one last time. Okay, I'm done. I'm done trying to make my lines look pretty. There we go. So this is x prime and this is y prime. All right. So we look up above at how this is defined, and it's still going to be a sine. So if it's still a sine, that means that my directrix is running perpendicular to my y, or perpendicular to my x-axis. And so we have a rotated conic. I still have my E. My E is still here. E is equal to 1. My E times D is still there. So E times D is equal to 2. E is 1. That means D is equal to 2. Now remember, this is a plus sign. So that means my directrix is going to be 2, 1, 2. And it's going to be perpendicular to the y prime. So that's where my directrix is. And if you recall, my focus is right here. Now, because my E is 1, I know I have a parabolic shape. Because I have a parabolic shape, what I also know is that this right here is where my vertex is. So I'm going to have some kind of parabolic shape that looks like that, although I'm sure yours is going to be drawn so much better than mine. And then there's one more example here where I am looking with a rotated axis. I know it's a rotated axis because of this. So I'm going to let you all try this one, and so that's the finishing of 11.6.